Hello. In this section, I will determine whether the graph is concave up or concave down and point of inflection using second derivative. So we are learning today concavity and point of inflection using second derivative. So let's say you had this graph f of x equals x to the fourth minus 4x to the third. With the second derivative calculus, you could actually figure out where the graph is concave up, concave down, and a point of inflection. So as you can see on the red, this section right here is concave up. Concave up is like this U shape, right? So this is concave up. And concave down is where it's like that, concave down. And I'll briefly talk about point of inflection. Basically, it's just where the graph starts to change between concave up and concave down. So yeah, the next thing is point of inflection. So what is a point of inflection? A point of inflection is when the graph changes from upwards to downwards concavity or downwards to upwards concavity. Okay, so as you can see, here are some examples of an inflection point. So you have, on this one, you have an inflection point because it changes from concave down to concave. This should be concave up. Yeah, so it changes from concave up to concave down, and then right here it changes from concave up to concave down, and here's another point of inflection. So basically, it's just it's the point where it's about to change from concave up to concave down or concave down to concave up. That's all it is. So now you know what it looks like on graph. Now let's figure out how to find it. So rules for finding concavity and point of inflection. So what I would do first is take the second derivative, not the first one, but the second, and find the critical, set it to 0 and find your critical points, right? And then just like where it was increasing, decreasing, we have to make a number line and apply the test point method. If the sign is positive, then it is concave up. If the sign is negative, then it's concave down. If the sign changes from positive to negative or negative positive, then you have a point of inflection at that specific critical x value. And step 3, if you have a point of inflection, sometimes you don't, sometimes you will, substitute the x values back into the original equation to find the y value, because a point in inflection is a coordinate. So that's why you have to, and always put it back into the original one. So let's do some examples. I think I'm only going to do 2. In the following examples, find where the graph is concave up or concave down. Also find point of inflection if you have any. So let's start with example 1. And then maybe I can like put this in Desmos to show you where, if it actually makes sense. So f of x equals x to the fourth minus 4x to the third. I think this is the one we did. So on the example. So first I would I got to take the second derivative. So first I got to take the first derivative, right? You can't take the second without taking the first. So the derivative of these are pretty simple. It's just power rule. So the derivative of x fourth is 4x cubed because of power rule. And then the derivative of negative 4x cubed is going to be negative 12x to the second. And then I'm going to take the second derivative of that. So the derivative of 4x cubed is 12x to the second. The derivative of negative 12x to the second is negative 24x to the 1. Okay. Now that you found the second derivative, find your critical points by taking the second derivative, setting it to 0, and solve for x. say I could take out a 12x. And then you're going to get x equals 0 and then x equals 2. Okay, so now that we know our two critical points, put it on a number line and we're going to apply the test point method. So our smallest x value is 0. Our more positive x value is 2. 1, 2, 3. We have 3 different boundaries we have to test. So remember, we're going to put it in f double prime, right? Don't test your values in the original problem. So put it in f double prime. So if you recall, f double prime is 12x squared minus 24x. So let's test boundary 1. So we need a number less than 0. So I'll use -1. So put that in your double prime. So that's 12, -1 squared minus 24 times -1. If you put in the calculator, it's 36, but just know it's positive, so that's the only thing I care about the most. So you're going to put a plus, plus, plus. And then in boundary 2, I got to test a number between 0 and 2, so I'm going to use +1. So that'd be 1 squared. So when you put that in the calculator, you get an output of -12. That is negative, so put a minus. And then I got to test boundary 3. I need a number greater than 2. So let's do f double prime of, let's try 3. So that's 12 times 3 squared. Now I get an output of positive 36. That's positive. Okay. So we can, okay, so now if you look at our sign chart, we do, okay, so where is it concave up? So it's concave up wherever there's a positive sign. So it's going to be from the intervals -infinity to 0. And this, you don't have to put a union, just put a comma, right? And then it's also concave up from parentheses to infinity. And then it's concave down from the boundary 0 to 2. Okay, and do we have a point of inflection? I think we do. The reason we do have a point, if you look at our sign chart, it changes from, we have a point of, so we have a point of inflection at the x value of 0 and 2. Why? Because if you look at it changes signs. So from positive to negative, it changed. And then from negative to positive, it changed. So you do have a point of inflection at the x value at x equals 0 and 2. Now you got to find the y value. So you're going to put these x values back into your original problem. So so if you plug in f of 0, this would be 0 to the 4th minus 4 times 0 to the 3rd, and that would be 0. And then let's try f of 2. That gives me an output of -16. So you have a point of inflection at the point 0, 0, and then 2, -16. So now let's actually see I guess we could just put in Desmo to see if it's true. 1 second, let me share screen. So here's our graph. Can you see it? So is it true? Is it really concave up from -infinity to 0? I believe so, right? If you look at this boundary, it has that little U shape barely. So it is concave up from -infinity to 0. And is it also concave up from 2 to infinity? I think so. Yeah. And is it concave down from 0 to 2? Yes, because if you look here, maybe if I zoom closer. Yes, it is concave down from 0 to 2. And then, yes, and then your point inflections are 0, 0, and 2, -16. So, yeah. Okay, now let's go back to the last example. So example 2, this is a rational function. So, and this one's a little bit more work when taking the second derivative because you do have to use the quotient rule. So yes, so let's first find the first derivative. So quotient rule, quotient rule is, if you forget, it's f prime of g minus g prime of f all over g squared. So what would be my f? My f value would be x. My f prime would be 1. And then my g would be x squared plus 1. My g prime would be 2x. So f prime of x equals to f prime, which is 1. And then g is x squared plus 1 minus bracket g prime is 2x. And then f is x all over g squared, which is x squared plus 1. So when we clean this up, this would be x squared plus 1. And then 2x times x, that's 2x squared. And then distribute that minus, that's minus 2x squared. All over x squared plus 1 squared. And when you clean that up, that would be, so 1x squared minus 2x squared is negative 1x squared plus 1. So unfortunately, we have to keep, so this is what f prime is. F prime of x, so we got to we got to take the second derivative. So let's see. So what would be my f? My f is negative 1x squared plus 1. So f prime would be negative 2x. And then g would be x squared plus 1 squared. And g prime would be 2 x squared plus 1. And then power rule, so this would be 1, and then take the derivative inside, so that would be 2x. So g prime would be 2x times 2, that's 4x, and then x squared plus 1. Okay, so let's take our f double prime. So f double prime of x is, it's going to be, well, so we have to apply the second derivative. So f prime is, we said it was negative 2x. And then g is x squared plus 1 squared minus bracket g prime is 4x times x squared plus 1 times by f, which is negative 1x squared plus 1 all over g squared. So that'd be x squared plus 1 square raised to the second. Yeah, it looks like a big mess. What would I do? You know what? What I would do is simplify the numerator, but do you see something you could take out? I do. I think you could take out, you can factor out x squared plus 1, because this is, think of this as one term and then this whole thing is one term, right? So you definitely can take out an x squared plus 1, and I think you can only take out 1 right now. So like if you focus here, if you take out an x squared plus 1, then you're left with, you need a negative 2x. And we also need an extra x squared plus 1. And then over here, we could take, since we're taking out x squared plus 1, we have the leftover of a 4x and this, right? And also, because we also have to distribute this minus, it's going to be minus 4x times this whole thing. And then on the bottom, when you raise a power, so x squared plus 1 squared raised to the second is actually going to be x squared plus 1 raised to the fourth. Okay. And then clean it up again. So I guess FOIL it out. So FOIL negative 2x squared times x squared is negative 2x cubed. Negative 2x times 1 is negative 2x. This would be positive 4x cubed. And then this would be negative 4x. All over x squared plus 1 raised to the fourth. Okay, continue cleaning this up. I think in the bracket, what we do, we can collect like terms. So 4x cubed and negative 2x cubed is positive 2x cubed. Negative 2x, negative 4x is negative 6x. And then what can we cancel? I think we could cancel x squared plus 1. So how much can we take out? This has a power of 1. So we could take this cancels, and then this just becomes a 3. So you're left with 2x cubed minus 6x all over x squared plus 1 to the third. And then what I could do also do on the numerator is take out a negative 2x. So that'd be negative 2x. This would be negative x squared plus 3. Okay, so this is our final f double prime of x. I know that was a lot of work. Now let's find our critical values. So set this to 0. Or the same, it's the same thing as 0 over 1, right? 0 over 1 is the same thing as 0. So I guess you could cross multiply. So 1 times this, it's itself, right? And then it's going to equal to 0 because 0 times this is just 0. Now, you do remember your critical points, I think from I stated in the last video, it's also where it makes the function undefined. So you do have to set your other equation would be x squared plus 1. You're going to set this to 0, right? Because that would make it undefined. So let's start with this one. Negative, if we set this negative 2x to 0, that would be negative 2x equals to 0. And then this would be negative x squared plus 3, set it to 0. And then over here, when you solve for x, you would divide negative 2. You get an x value of 0, right? And then over here, you're going to subtract 3. Subtract 3, I get negative x squared equals to negative 3. Divide this by negative 1, negative 1. So this is going to be x squared equals to positive 3. And when you take the square root, you get two values, right? For the positive root and negative. So your other, it's going to be radical 3, and then your other one is going to be negative radical 3, and then your x value, your other is 0. So we have a total of 3 critical values. This one we can't use. You know why? If you try to solve for x, I would have to raise everything to the 1/3. I get x squared plus 1 equals 0. Solve for x by subtracting 1. And that's where we have a problem. When you take the square root of negative 1, it's no longer real. So we can only use real numbers, so this is not real. So we can't use that anymore. Okay, so now what we do is put it on the number line, right? Our smallest x value is negative radical 3. More positive one, second positive one is 0, and then the other one is positive radical 3. So we have 1, 2, 3, 4 boundaries to test. So put it in the double prime. So if you f double prime of x is negative 2x okay, and then so let's test boundary 1. Well, negative radical 3 is about negative radical 3 is about negative 1.7. So I need a number less than that. So maybe I could use negative 3. So when you put negative 3 into the function, you get negative 2 times negative 3 bracket minus 3 squared plus 3 bracket negative 3 squared plus 1 to the cubed. Now, I don't really care about the number, I just care about the sign. So when you do this out, when you do the numerator, it becomes a positive. And then on the bottom, it becomes a negative. And we know that a positive over a negative is negative. So in boundary 1, it would be minus. Okay, now let's test boundary 2. So I need a number between negative radical 3 and 0. I could use negative 1.2. So yeah, so when you put this in the calc, I'm not going to do the work. It just says that it's going to be a positive on the top, and then on the bottom it's going to be positive. So a positive or a positive is positive. And then boundary 3, I need a number between 0 and radical 3. So maybe I could use 1.5. So when you put it in the second derivative, the numerator will become negative, and then on the bottom, it's going to be positive. So a negative over a positive is negative. So we're going to put a minus. And then let's test boundary 4. I need a number greater than radical 3, so maybe I'll just stick with 3. So when you put that in, you get 0 on the top, and then on the bottom it becomes positive. So we know that 0 over a number is always going to be 0, right? So 0 is still technically positive. So we'll just put the boundary 4 would be positive. So it is increasing in boundary 2 and boundary 4, and it's decreasing from boundary 1 and boundary 3. And we actually have 3x values of point of inflection, right? We have a point of inflection at the x value of negative radical 3, at the x value of 0, and positive radical 3, because if you see the sign chart, it changes from negative to positive, negative. So we said that it is concave down at negative infinity to negative radical 3, right? Because it's negative sign. And the other one, put a comma, and I'll use 0, radical 3. And then it's also concave up from minus radical 3, 0 to radical 3 to infinity. And then you do have a point of inflection. At 3x values, right? One is at negative radical 3, 0, and then radical 3. So you do got to put, to find the y value, you do got to put it back into the original equation. So if you plug in negative radical 3 into the original problem, it would be negative radical 3. And then that would be negative radical 3 over 4. And then when you plug in 0 back into the original problem, you do get an output of 0. And then when you plug in radical 3, you get radical 3 over radical 3 squared plus 1. So that would be radical 3 over 4. Okay, so concave up, down, concave up in this boundary. And we have a point of inflection in these 3 points. Okay, so point inflection right there. And if you don't believe me, you could just put it in Desmos to see if it's true. It is true though. Okay, that's it for today's section. Thank you. Have a great day. Bye-bye.